welcome to today's lecture for analytical chemistry. Today we are going to go through lesson 4, which is about extraction techniques. Now take out our lecture notes and get ready for today's lesson. Today we are going to learn about the principle of extraction process. At the same time, we will do some calculation on distribution coefficient, also known as the KD. And we'll also calculate the percentage extraction in a liquid-liquid extraction process. Next, let's go through the principle of the extraction process. Now, in extraction, we have a solute which is being dissolved in a solvent. And this solute is being extracted into a new solvent while achieving an equilibrium. Now, sometimes we can term the solute as the analyte. So we want to extract this analyte using a new solvent, and the glassware is actually a separatory funnel, and we can also term the whole process as liquid-liquid extraction. Why liquid-liquid extraction? Because two solvents are involved, okay? One, the original solvent, okay, original solution, okay, and two, the fresh solvent, and sometimes we can also term it as the extracting solvent. Okay, so extracting solvent is the one that we use to extract the solute, okay, from the original solution. So two solvent is involved, so we have liquid-liquid extraction. Now I can show you a diagram here. This is actually a separatory funnel, okay. So this glassware is being used in our liquid-liquid extraction process. So what happened is we have two types of liquid, okay. One, which is the original solvent containing the solute, and number two is the extracting solvent, okay, the solvent that we want to extract the solute out. So in this process, what happened, you can imagine the solute, okay, in the original solvent. Okay, so all these are actually the solute, or we term it as the analyte, and then we will add in the extracting solvent into the separatory funnel. So in the process, we will do a good shake. And what happened is the solute will get extracted, okay, into the extracting solvent. Now this process, okay, is not a one-way process, it's a two-way process. So the solute will travel from the original solvent to the extracting solvent until it reaches an equilibrium. Okay, when it's done, what happened is the extraction is completed, and we can actually on the tap to allow the illusion of a higher density liquid, which is at the bottom layer. Okay, so later we will go through this, and you will realize that when to allow this process to happen, the liquid-liquid extraction must have two liquid of different density, such that the high density liquid will be at the bottom, whereas the top layer will have the low density liquid, and then you'll extract it layer by layer. So these two liquids should not mix. At the time of initial contact, what happened is the solute will move from the original solvent to the extracting solvent at a particular rate. All right. And at some time, what happened is the solute may move back to the original solvent. Like what I mentioned just now, this is not a one-way reaction. Okay, the solute can travel both ways until it reaches an equilibrium. All right. And we will term this equilibrium as a distribution coefficient, KD. If the solute is more soluble in the extracting solvent, which is what we want, a large amount of solute will be found, or we say transferred to the extracting solvent, okay, from the original. That means most of the solute we want it to be extracted by the extracting solvent. So this is actually what we want to achieve. We want the solute to be extracted by the extracting solvent.
Liquid-liquid extraction is an important purification technique in organic chemistry in which two immiscible solvents are needed. Methyl terbutyl ether and water are common solvents used in a liquid-liquid extraction. The extraction process takes place in a separatory funnel. Before adding any liquid, remember to check that the stopcock is closed, then add the two solvents into the separatory funnel. The liquid-liquid extraction consists of two phases. an aqueous phase and an organic phase. These two phases are immiscible and form distinct layers. To be able to extract the desired compound, in this case fluorinone, the compound must be soluble in one solvent and be insoluble in the other solvent. The fluorinone is more soluble in ether. Place the stopper in the separatory funnel. Securely pick up the funnel and invert, keeping one hand on the stopper to make sure it's securely in place. Slowly open the stopcock and allow for any pressure built up in the separatory funnel to be released. Once pressure has been released, close the stopcock and shake the separatory funnel. Again, invert the separatory funnel and release any gas that has built up. Repeat this process several times until pressure is no longer released when opening the stopcock. Place the separatory funnel back onto the ring stand and wait for the two layers to form. In this case, the denser solvent is on the bottom, while the less dense solvent is on the top. Once the layers have settled, remove the stopper from the separatory funnel and drain the desired organic layer from the funnel. Perform additional extractions and washes as necessary. Remember to discard any excess liquid in the appropriate waste container.
Okay, I hope that you have a better understanding of the liquid-liquid extraction process after watching the video. Now, this is a diagram that summarizes the whole extraction process using the separatory funnel. Now, usually this liquid-liquid extraction will consist of two different types of liquid, all right, with different density. The less density liquid will be found at the top layer, whereas the more dense liquid will be found at the bottom layer. Okay, so for example, diagram 1, we have the solvent being the oil, and the density is 0.8, whereas the other solvent is water and the density is 1. So we can see that from the density, oil being a lower density will be found at the top layer. All right. Example 2, we have water as the solvent, density is 1, and chloroform as the other solvent, density 1.5. So with this, okay, now the water having lower density, it will be found at the top layer. Density has to be different so that you know you can identify which is the top or bottom layer. Another thing is the polarity has to be different such that the two solutions will not mix. All right. So if you have water as one of the solvent, water is polar. The other solvent has to be non-polar so that they do not mix. All right. So if both solutions are polar, this liquid-liquid extraction cannot take place because both liquid will be able to mix and then you cannot see the formation of two layers. All right. So always take note, liquid-liquid extraction can only take place where number 1, density of the liquid has to be different. And number 2, they must also have a different polarity. Okay, so one being polar, one being non-polar, so that these two liquids do not mix. All right, so the keywords is the two liquid should not mix. Let's move on to the distribution coefficient, KD. Now, when equilibrium is being reached, the solute distribution can also be defined as the distribution coefficient, KD. It is being calculated as the ratio of the concentration of solute in the extracting solvent to the concentration of solute in the original solvent. Now, it may sound complicated, so let's try to explain this using a diagram. So let's imagine this as the liquid-liquid extraction setup, and this being the separatory funnel. So at first, what we have is the black color particles being the solute, and they are found in the yellow color original solvent. Okay, so in all the red color dots, we just concentrate on the solute, which is the black color particles, and we want to extract the solute, okay, using fresh extracting solvent. So during the extraction process, I pour in some extracting solvent. Now, when this happens, okay, I'll do a shake, and what happens is the solute will travel to the extracting solvent and get extracted from the original solvent. Now, remember, this is not a one-way process. Some of the solute may travel back to the original solvent. So it's a two-way process, and they will continue until it reaches equilibrium, whereby there will be a fixed concentration of solute in the extracting solvent and the original solvent. So when this happens, the concentration of solute in the extracting solvent divided by the concentration of solute in the origin solvent, this is actually the Kd value. All right. So Kd is calculated as the ratio of concentration of solute in the extracting solvent, which is the top layer, divided by the concentration of the solute in the original solvent, which is the bottom layer. So there will be a value, which is the Kd. So we can rephrase this whole statement, okay, using a formula. So Kd equals to concentration of solute in the extracting solvent divided by concentration of solute in the original solvent. Let's look at the formula before we start working on the question. Kd equals to concentration of solute in extracting solvent divided by concentration of solute in the organic solvent. For Kd value is given as 98%. But we cannot substitute this value directly. We need to convert it to a ratio. So 98 divided by 100, which in this case is 0.98. Yeah. So concentration of solute in the extracting solvent, you can substitute as 0.0127, whereas concentration of solute in the original solvent, which is in the water, you can let it be X value because you do not know what's the unknown. So with that, let's work on the question. We have 0.98 equals to solute in extracting solvent 0.0127 divided by the X value. Then we solve for X. Let this be over 1. We can cross multiply. So you will get 0.0127 equals to 0.98x. So how to find the X value? You can bring 0.98 to the other side of the equation by dividing over. So you will get 0.0127 divided by 0.98, which is equals to X. So key in the value in the calculator, your X value should be 0.0130 M. So remember, follow the question, round off your answer to 4 decimal places, and always remember to input your unit. So for concentration, unit is in molarity. Now in example 2, you are given Kd as 231. The weight of analyte found in 75 ml of aqueous solution after extraction was 0.0723. And then the question also says, find the weight of analyte in 50 ml of extracting solvent. All right. And you are supposed to present your answer in 2 decimal places. Let's try to annotate the question. Now you are given Kd 231, so you can substitute 231 in the Kd. And they told you 75 ml of aqueous solution. Now aqueous solution is also known as the original solvent. Okay, meaning at the denominator, you know that you have 75 ml and the amount of analyte is 0.00723 gram. Okay. Next, you are supposed to find the weight of analyte in 50 ml of extracting solvent. So numerator, you know you have 50 ml of extracting solvent, but the amount of analyte you don't know. So let it be X. So you're supposed to find the unknown X. So with this, let's try to substitute into our equation. So you know that Kd is 231 equals to concentration of solute in extracting solvent. Now, concentration can also be equals to mass divided by volume. So in this case, they didn't really give you the concentration in molarity. Instead, they gave you the weight and the volume. So concentration can be equals to X divided by 50. Okay, for the first part. Now for the second part, you're supposed to divide Divide by what? By the solute in original solvent. Now, same thing. They didn't give you molarity, but you have the weight and the volume. So you take the weight, divide by the volume, which is 75. What you can do is you can bring this whole term to the other side of the equation. It's a divide. You bring over is a times. So it becomes 231 times 0.00723 divided by 75 equals to x over 50. So this is like maths, all right? And then how to find your x? This is divided by 50. You can bring over times, meaning what? You can rewrite as x is actually equals to 231 times 0.00723 over 75. Then the 50 is divided, bring over times another 50. Yeah, so keep this value in your calculator. You should get your final answer as 1.1134 gram. So they want to answer in 2 decimal place. So round off to 1.11 gram, 2 decimal places. Okay. Now let's try to understand the question first by drawing a diagram. Now imagine before extraction, you have benzene at the top layer because benzene has lower density compared to water. And inside, you have 100 ml of benzene and 100 ml of water. So this is before extraction. Before extraction, that means you haven't shake, meaning 3 grams of iodine is found in the water layer. So after extraction, that means you shake the separatory funnel. What happened is top layer should still be your benzene, okay, because density, and bottom layer should be your water. What happened is some of the iodine layer get extracted by the benzene, yeah, and then it shows that 1 gram is found in the water layer. Okay, so iodine, out of the 3 gram iodine in water, some of them traveled to the benzene layer and you're left with 1 gram, meaning benzene layer got how much iodine? It should be 3 minus 1, which is 2 grams of iodine on top. Yeah. So before extraction, what happened is iodine is found in the original solution, which is in the water layer. Then it goes through liquid extraction. So after extraction, you'll find that some of the iodine traveled to the benzene layer. Yeah. And 1 gram is at the water layer, meaning what? 2 grams must be at the benzene layer. So that when you add 2 plus 1, it should go back to 3 grams, which is the original amount. All right. So when we substitute into our KD equation now, we need to take note. This KD equation is for after extraction. Okay. So KD, you're supposed to find KD. KD should be equals to concentration of solute in the extracting solvent. In this case, extracting solvent, you have 2 grams. And then original solvent, solute in the original solvent, you should have 1 gram. Yeah, so KD should be 2 divided by 1. In this case, answer is 2. Okay, so KD, no unit because KD is dimensionless. So do not put unit for KD. Yeah. So let's look at the my connection answer. So similarly, my connection, they took 3 gram minus 1 because at first you have 3 grams of iodine and then 1 gram left in the water. That means 2 grams is being extracted by the extracting solvent. Substitution is based on after extraction. Yeah. So moving to example 4. So the question says that KD is 169 for a given solvent extraction. What is the molar concentration of analyte found in the extracting solvent if the concentration in the original solvent after extraction is 0.0270. You're supposed to present your answer in 4 significant figures. So take note, always present your answer as per what the question requested. Now we look at the formula and we try to do our substitution. So KD from the question is 169. Concentration of solute in the extracting solvent. This is what you need to find. So you can let it be X molar. And then next, you know that in original solvent, you have 0.0270 molar. So I think this question is quite straightforward. You just need to substitute the numbers. 169 equals to X over 0.0270. Yeah. So you can do a cross multiplication. Yeah. So X times 1 is X. Then this part is 169 times 0.0270. So key the values in your calculator. Your answer should be 4.563 molar in 4 significant figures. So you can double check your answer with the mind connection answer. And don't forget your unit in molarity. Next, we have percentage extraction. Now for percentage extraction, let's look at the definition. It will help us determine the efficiency of the extraction process. Now please take note that extraction is never 100%. Yeah, you can never 100% extract the solute using the extracting solvent. Usually you need to do multiple extraction. So how to find the percentage efficiency of the extraction? Usually we take mass of the solute in the extracting solvent. That means what we extracted out, divide by the mass of solute in the original solvent before extraction. That means originally how much solute is there. So take the amount that you extracted, divide by the total amount in the original solvent times 100%, you'll get your percentage extraction. And the unit for this case will be in terms of percent. Yeah. Let's try one question and then you'll have a better understanding how the formula works. For this question, it says that in the extraction experiment, 0.0376 gram of analyte is extracted into 50 ml of solvent, yeah, from 150 ml of water sample. So define the different solvent. So this solvent must be my extracting solvent because I use this to extract my solute or the analyte. So sometimes if you're confused, analyte is actually my solute. Yeah, what I want to extract. So my water is actually my original solvent. Yeah. So at first, there are 0.0192 gram of analyte in this volume of water. So you are supposed to calculate the KD and next part, calculate the percentage of analyte extracted. That means your percentage extraction. Yeah, this one asks for percentage extraction. And present your final answer in 2 decimal place. So you need to find 2 things here. Number 1, KD. Number 2, percentage extraction. Given the KD formula, let's try to do some substitution. Now, based on the question, it says that 0.0376 gram of analyte is being extracted into 50 ml of solvent. So this solvent actually refers to your extracting solvent, meaning the numerator, you can substitute 0.0376 gram, yeah, and the volume of solvent is 50 ml. Next part, you have concentration of solute in original solvent. Now, they mentioned that at first, there are 0.192 gram of analyte in the original solvent in the water. But take note, your KD is for after extraction. This value of analyte is for before extraction. Remember the previous question about the iodine? Meaning to find the concentration of solute after extraction, you need to minus. Take 0.192 gram minus 0.0376. Yeah, so the total amount of solute minus what is being extracted to get this value, which is left in the solution after extraction. So you are supposed to substitute this value instead. Yeah. And what is the volume of water? It says you have 150. Yeah. So with this, let's substitute into our KD equation. KD, you do not know what's the value, but you know that the concentration, take the weight, divide by volume for the extracting solvent. Yeah. Take this, divide by the weight in the original solvent, which is 0.1544, divide by 150. Yeah. So take note, just now we also mentioned, when you want to look at concentration, you should take mass divided by volume. Yeah, concentration is mass divided by volume. So I take the mass of the solute in extracting solvent, divide by the volume, then the whole thing divide by mass of the solute in original solvent after extraction, divide by volume. So key in the values in your calculator and you should get 0.73 in 2 decimal places. Take note, KD, no unit, dimensionless, because you cancel off the unit. Yeah, concentration in this case is gram per ml. Concentration for the bottom is also gram per ml. So you cancel off the unit. KD is dimensionless, no unit. Next, let's move on to part 2 of the question. Part 2 wants us to find the percentage of analyte extracted. Now, based on the equation, percentage extraction equals to mass of solute in the extracting solvent. Now, in the extracting solvent, we found that there are 0.0376 gram of analyte. So remember, this is what we extracted. And then the mass of solute in the original sample. So this was the analyte in the original sample. Remember, before extraction, the total amount of analyte. So we are supposed to substitute this value as the denominator and then times 100%. So let's rewrite this whole equation. Percentage extraction equals to the amount being extracted, in this case 0.0376, divided by the mass in the original solvent. It's the mass of solute in the original solvent. So this part here, we need to substitute the value before extraction because we want to know the total amount of solute before extraction. So when the previous question, when you find the KD, it is after extraction. So you need to minus. For this one, when you substitute, you want the mass of solute in the original solvent before extraction. So you don't minus. Then everything plus 100%. So key in this value in your calculator, you should get 19.58% in 2 decimal place. So take note, you have unit as percentage, and then based on the question, present your answer in 2 decimal places. So you can check your answer against my connection. Just take note that when you substitute the values in your KD, this is for after extraction. So after extraction, the amount of solute in the original sample, you need to minus, yeah, because some of the solute get extracted out, so it become lesser. Whereas when you want to find the percentage extracted or percentage extraction, the amount of solute in the original sample should be before extraction. That means the total amount. Okay, so this is the difference. Please take note. With this, let's summarize. So today we learned that extraction can never be 100%. So each extraction will have a specific distribution coefficient, which is also known as the KD. Now, when there is more interaction between the extracting solvent and the dissolved solute, you will have better extraction. And usually, because extraction is never 100%, we will prefer multiple extraction when it comes to liquid-liquid extraction and using smaller volume extracting solvent. These are the two equations that we learned, and then we also did some examples on how to calculate, for example, the KD. So KD refers to the concentration of solute in the extracting solvent divided by concentration of solute in the original solvent. And for percentage extraction, this one helps us to calculate the efficiency of the extraction. So we will take the mass of solute in the extracting solvent divided by mass of solute in the original solvent before extraction. Yeah, so that means it's the total amount of the solute in the solvent before you do your liquid-liquid extraction. With this, I shall end my lecture 4. If you have any question regarding today's lecture, please approach the teachers when you see them during the practical lesson or face-to-face lecture.